So let's say that y is equal to x squared plus 1 to the power of 6. And let's differentiate this. Now, to do this, we need to use something called the chain rule. And we can use the chain rule when we have a function inside another function. This can be a bit difficult to explain, but basically, we have this x squared plus 1 here, which is a function, inside this power of 6 here, which is another function. So therefore, we can use the chain rule. And the chain rule is that dy over dx, so this is what we want, dy over dx, the derivative, is dy over du multiplied by du over dx, where u is a substitution that we make for the inner function, and this is the function inside the other function. The easiest way to explain this is by showing you. So in this example, the inner function is this x squared plus 1. So we're going to say that u is equal to x squared plus 1, because this is the inner function. And therefore, we can rewrite this as y is equal to, instead of x squared plus 1 to the power of 6, we can write it as u to the power of 6, as u is equal to x squared plus 1. Okay, so in order to find dy over dx, we first need to find dy over du. Now, we talked about this in the year 1 differentiation video. I just want to give you a very quick reminder of what the terminology means of dy over du and dy over dx. For a very simple example, if y is equal to x squared, then dy over dx is equal to 2x. The bit on the top, the dy, this is the thing that's actually being differentiated, so the y is being differentiated. And the bit on the bottom, the dx, this is what we're doing it in terms of. So we're doing it in terms of x. These are like the parts that are actually being differentiated. So x squared becomes 2x like this. So if we have dy over du, the bit on the top dy is what we're differentiating. So we're differentiating y. And the bit on the bottom, the du, this is what we're doing it in terms of. So we're doing it in terms of u. The best way to think about this is that the u becomes the x. So this is the u here, and it becomes the x. So this is basically the equivalent of x squared. So dy over du is equal to, so u to the power of 6 becomes 6u to the power of 5. So this is dy over du. And now we need to do du over dx. So du over dx is equal to, so du, the bit on the top, is what we're differentiating. So we're differentiating u. And the bit on the bottom, the dx, this is what we're doing it in terms of. So we're differentiating the x, so the x squared plus 1. So we're differentiating this, so this is going to become 2x, and then when you differentiate a constant, it just goes away. So du over dx is equal to 2x. Now, the chain rule is that dy over dx is equal to dy over du times du over dx. So therefore, dy over dx is equal to dy over du, which is 6u to the power of 5, times du over dx, which is 2x. And this can be simplified to 6 times 2 is 12, so it's 12 x u to the power of 5. Now, the important thing is that we cannot have u in our final answer, because this is a substitution that we made. We need to get rid of the u, and we need to substitute back in the x squared plus 1. So this is equal to 12x, and then we substitute back in x squared plus 1, x squared plus 1, and then u to the power of 5, so it's x squared plus 1 to the power of 5. So dy over dx is equal to 12x x squared plus 1 to the power of 5, and that's how we do the chain rule. To remember the chain rule, you can think of it like the du parts kind of cancelling out like this here, like it's a fraction. You just leave dy over dx. In reality, that's not actually how it works with differentiation and why the chain rule works, but this is the way that I remember it, with the du's cancelling out. So here's another example where we have y is equal to sin cubed of x. To make it easier to understand why we want to use the chain rule on this, I'm going to rewrite this as sin x to the power of 3. These two are the same thing, it's just different ways of writing them. And hopefully you can see that the inner function is the sin x and the outer function is this power of 3 here. So we're going to make u the substitution for the inner function, which is sin x, and therefore we can write y as sin x is u, so this is u to the power of 3. Okay, so for the chain rule, we need dy over du. So dy over du is going to be equal to, and then it's going to be u3 differentiated, which is going to be 3u squared, and then du over dx is going to be sin x differentiated. And we talked about in the first video in this chapter how we differentiate sin of x. Sin x differentiated is cos of x. So therefore dy over dx is going to be equal to dy over du, which is 3u squared, multiplied by du over dx, which is cos x, like this. Now again, we want to replace the u at the end, so we're going to rewrite this as 3, and as u is sin of x, this is going to be u squared, so it's going to be sin squared x cos x. So dy over dx is equal to 3 sin squared x cos x. So here's another example. Now, the way I've shown so far is basically the long way of doing the chain rule, where you do the u substitution, then you write it out, etc. The way that I and a lot of people do the chain rule is sort of quicker than that. You don't worry about the u substitution, you don't worry about this formula up here. You just think of it as the inner and outer function. And the derivative is just the inner function differentiated multiplied by the outer function differentiated. So for this question, for example, it's dy over dx is going to be the inner function differentiated, and the inner function is the x to the power of 3 plus 3x. So therefore the inner function differentiated is going to be x to the power of 3 differentiated, which is 3x squared, plus 3x differentiated, which is 3, like this here. So this is the inner function differentiated, and then we multiply it by the outer function differentiated, and the outer function is this to the power of 5 here. And we sort of treat this like it's y is equal to x to the power of n, and dy over dx is equal to nx to the power of n minus 1. So when we differentiate this outer function, this 5 is going to come down here, and then it's going to be, now when we differentiate the outer function, we have the inner function here, and basically it's constant. We don't touch it, we don't differentiate it in any way, we just write it out, so it's x to the power of 3 plus 3x, like this here, and then this 5 is now going to be n minus 1, so it's now going to be 4, like this here. And then this is dy over dx, we can simplify it to 5 times 3x squared plus 3 times x to the power of 3 plus 3x to the power of 4, like this. I just want to exaggerate the thing again with when we're differentiating the outer function, is we have the inner function present, but we don't touch it in any way. If you want to, you can think about it like the u substitution. If we substitute in u here, so it's u to the power of 5, this here is going to be 5u to the power of 4 when we differentiate it. This u here we don't touch, so therefore this x to the power of 3 plus 3x is still present here. We don't touch it in any way when we're differentiating the outer function. Now, these two methods that we've shown in this video are obviously the same thing. They are both the chain rule. They are just two different ways of thinking about it, with this one being quicker. I've written out the full longer way of doing it here. Now, if you want to use the longer method with the u substitution to ensure that you get the right answer, especially if you're very new to the chain rule, that's completely fine. For the rest of this video, I'm going to be doing it the shorter way, but it's completely fine for you to do it the more full-on way if you want to. So here's some more examples of when we need to differentiate using the chain rule. So for the first one, cos of x squared, the inner function is this x squared and the outer function is this cos here. So therefore dy over dx is going to be the inner function differentiated, which is going to be x squared differentiated, which is going to be 2x, multiplied by the outer function differentiated, which is going to be cos differentiated, which is going to be equal to minus sin. Remember, the thing I said before is that when you differentiate the outer function, this inner function is the same, so this is still going to be sin of x squared, like this here. Don't forget this is here like it is up here as well, and if you simplify this, this is equal to minus 2x sin of x squared, like this here. For the second one, 2e to the power of sin x. I talked about this in the first video in this chapter. When you have a coefficient in front of the thing that you're trying to differentiate, the only effect that this has is, so remember, this is 2 multiplied by e to the power of sin x. If we do dy over dx, this coefficient is going to be transferred down here as well, so it's going to be 2 multiplied by, and then we individually differentiate this. This is the only effect the coefficient has, we just transfer it down here as well. So it's going to be 2 multiplied by, and then we differentiate this here. The inner function is the sin x, and the outer function is this e to the power of. So the inner function differentiated is sin x differentiated, which is cos x, and this is multiplied by the outer function differentiated, which is this e to the power of. And when you have e to the power of something, there's no effect, so it's still going to be e to the power of sin x, like this here. Don't make the mistake of thinking this sin x is going to come down here like it's e to the power of kx. The reason is because if you did this the long way of the chain rule and you replace this sin x with a u, this is e to the power of u, and if you do y is equal to e to the power of u, dy over du is just equal to e to the power of u. This u doesn't come down here, so therefore this sin x doesn't come down as well. If it was something like e to the power of 2 sin x, for example, then this 2 would come down here like that. But because this sin x is like this, and this is the inner function, this does not come down when you're differentiating the outer function. And therefore, if you simplify this, this is equal to 2 cos x e to the power of sin x, like this here. And then for the third one, 3 times the natural log of cos of x. Dy over dx is going to be, so this coefficient transfers down again, so it's 3 multiplied by. The inner function is this cos x, and the outer function is this natural log. So the inner function differentiated is cos x differentiated, which is minus sin x, and this is multiplied by the outer function differentiated, which is this natural log differentiated. And remember back to the first video in this chapter, when you differentiate a natural log it becomes 1 over x, but because we've got cos x here as the inner function, it's going to be 1 over cos of x here, because when you differentiate the outer function, the inner function is still present. And then if you simplify this, this is going to be equal to minus 3 of sin x over cos x. Remember, sin x over cos x is equal to tan x. So this is equal to minus 3 tan x. So here's another example, and this time we have an equation that has multiple terms in it, and we've talked about this before. When you have an equation that has multiple terms in it, you just differentiate each term individually. Now we have this square root here, and we also have this 1 over fraction here, and when we have this, it's easier to write it in the indices format here because it's easier to differentiate. So the square root is a half, and this 1 over x is going to be x to the power of minus 1. Revise the indices laws if you need a reminder of this. So therefore, we're going to differentiate each term individually. So if we start with this term here, so the inner function is this x squared minus 2, and the outer function is this power of half here. So the inner function differentiated is going to be this x squared minus 2 differentiated, and if you differentiate x squared, you get 2 x, and if you differentiate minus 2, as it's just a constant, it's just going to go away. So this is x squared minus 2 differentiated, and then we need to differentiate the outer function, which is this power of a half here. And when you differentiate a power of half, this half comes down as the coefficient, and then this inner function is going to stay constant like this, and now it's going to be to the power of a half minus 1. It's going to be to the power of minus a half, like this here. And we can simplify this because this 2 is going to multiply this 2 denominator here to cancel it out, so we're just left with x and then x squared minus 2 to the power of minus a half, and then we write this back in the square root format. This x is going to be in the numerator, and then this x squared minus 2 is going to be in the denominator because we have this minus power here, and it's going to be square rooted because of the power of a half here as well. So this is this term differentiated here. And then if we differentiate this sin of x minus 1, so the inner function is this x minus 1 and the outer function is this sin here. So the inner function differentiated is going to be this x the minus 1 differentiated, which is going to be, so this minus 1 is going to come down as the coefficient, and then it's going to be x, and now it's going to be to the power of minus 1 minus 2. So it's going to be to the power of minus 2 now, and then this is going to be multiplied by the outer function differentiated, so this is going to be this sin differentiated, and when you differentiate sin you get cos, and then it's still going to be the inner function is going to stay the same, so it's still going to be this x to the power of minus 1 like this here. And we can simplify this because this x to the power of minus 2 is going to be 1 over x squared, so it's going to be in the denominator like this here, and then this x to the power of minus 1 is equal to 1 over x. So therefore dy over dx is just going to be these differentiated terms added together. So dy over dx is going to be equal to this here. Now, really quick, I've already talked about this in the first differentiation video in this chapter, titled Differentiating Sin, Cos, Exponentials and Logarithms, and I recommend going back to that video for a bigger explanation on this, as I'm going to shorten it here for time. There's a really good way to check your answers to differentiation questions in an exam by using your calculator. So let's show how it works by doing this example here that we just figured out. So on your calculator, if you press shift and then this integration symbol here, you get this differentiation term. term. And if you put in the y value that the question wants you to differentiate, so in this case it's this expression here, so put this expression into your calculator, you can get the x terms by using this x button here on your calculator. And then if you put in a random value here for the x is equal part, so let's just say x is equal to 5 for example, if you press equals on your calculator gives out a value of 1.0034. So what this value is your calculator differentiating this expression here and then subbing in x is equal to 5 into the resulting derivative. So why is this useful to us? Because what we can do is we can sub in the same x value, so x is equal to 5 in this case, into the derivative that we figured out ourselves earlier using the chain rule and using maths. So that's what I've done down here. So I've subbed in for all of the x values, I've subbed in 5. And then if you put this into your calculator, it gives out a value of 1.0034. So this value is given out by your calculator differentiating this expression itself and then subbing in the value of x is equal to 5. And this value is given out by us subbing in x is equal to 5 into the derivative that we figured out ourselves earlier. And if these two values are the same, this tells you that this derivative that we figured out is correct. It's the correct answer. We haven't made any mistakes in our working out, and we can move on to the next question. Now, obviously, you can't just use this in order to solve the question. One, because it doesn't work like that. It doesn't give out this expression here. But even if it did, the examiners are aware that you have this calculator that's able to do this. So obviously, if you just wrote down the answer, they would never allow it. You need to show you're working. But what this is really useful for, this method, is after you've done the question like we've done before and you've got out this value here, this expression, use this method to get out these two values. And if these two values are the same, this tells you that you haven't made any errors in your working out. You've done all the working out on the maths correctly, and you can move on to the next question. Let's say that we're given this question here where x is equal to y to the power of 4 minus y, and we need to find dy over dx. Now this is a weird equation because x is actually the subject and it's written in terms of y instead. Now you might be tempted to rearrange this in order to make y the subject and then differentiate from there in order to find dy over dx, but you can't do that. There's no way in order to make y the subject here for this equation, so you can't do it like that. However, what we can do is we can find dx over dy instead. Now this is not what they want as the final answer, they want dy over dx, but we can find dx over dy, and I'll explain in a sec why this is useful to us. So we've already talked about this terminology in this video. When we have dx on the top, this means that we're differentiating x, and when we have dy on the bottom, this means that we're doing it in terms of y. Basically the x and the y kind of roles have swapped around, and we're actually going to be differentiating the y as if it's the x. So dx over dy for this equation here is going to be equal to, so y to the power of 4 is going to become 4y to the power of 3, and minus y is going to become minus 1. So dx over dy is equal to 4y cubed minus 1. So we have dx over dy, but we need dy over dx. And we can get this because of the fact that dy over dx is equal to 1 divided by dx over dy. Now you can think of this like a fraction and the kind of fraction flipping here because it's divided. Again, like the chain rule, this isn't actually mathematically how it works, but it's a fine way to remember it like that, is how I do it. So therefore we can say that as dy over dx equal to 1 divided by dx over dy, dy over dx in this instance is equal to 1 divided by dx over dy, which is 4y cubed minus 1. And we can rewrite this here as 4y cubed minus 1 under 1 like this here. So dy over dx is equal to 1 over 4y cubed minus 1. It's a bit unusual because it's written in terms of y instead of x, but this is actually fine. You are allowed, this is the final answer and this is a valid final answer. It doesn't actually have to be written in terms of x unless it specifically says so in the question, but here it doesn't specify, so we can write it in this form here. So here's another example like this, where x is equal to sin root y, and therefore we need to find dy over dx. Now, in this particular equation, it is actually possible to rearrange this to make y the subject, but the problem is the equation that you're going to get out is going to be very complicated and very difficult to differentiate, such that it's a lot easier to just leave it in this form here and find dy over dx using the method that we talked about before. So this here, with x being the subject, we can find dx over dy. I'm going to rewrite this using the indices law of y to the power of a half instead of root y, because this is a lot easier to differentiate. So therefore we can find dx over dy, and if we differentiate this, we're going to need to use the chain rule, with the inner function being y to the power of a half and the outer function being this sin here. So dx over dy, if we differentiate this, is going to be the inner function differentiated, so it's going to be y to the power of a half differentiated, which is half y to the power of minus a half, and this is multiplied by the outer function differentiated, so this is going to be sin differentiated, so this is going to be cos, and remember that this here stays the same, it's going to be y to the power of a half, like this, and we can quickly rewrite this using the indices law, with the numerator being cos of root y, and because we've got this y to the power of minus a half, this can be root y in the denominator like this, with the half like this here, and because dy over dx is equal to 1 divided by dx over dy, dy over dx is equal to 1 divided by this here, and this will just flip the fraction, so dy over dx is equal to 2 root y over cos root y. So for the rest of this video, I'm going to go through past exam questions to do with the chain rule. So for this one here, we need to differentiate with respect to x 5 plus x squared to the power of 3 over 2. So dy over dx is equal to, so we need to use the chain rule for this, with the inner function being 5 plus x squared and the outer function being this power of 3 over 2. So it's the inner function differentiated, which is 5 plus x squared differentiated. When you differentiate 5 as a constant, it just goes away, and if you differentiate x squared, it's 2x, and this is multiplied by the outer function differentiated, so this is this power of 3 over 2 here, so this is going to come down as the coefficient, and remember that the inner function stays here undifferentiated, so this is 5 plus x squared like this, and then it's going to be 3 over 2 minus 1, which is a half. And we can simplify this because this 2 is going to cancel out with this 2 to leave us with 3x, and then we can write this as the square root of 5 plus x squared. So dy over dx is this expression here. So here's another exam question where we need to differentiate with respect to x plus the natural log of 2x to the power of 3. So dy over dx is going to be, so we're going to need to use the chain rule when the inner function is x plus the natural log of 2x and the outer function is this power of 3 here. So dy over dx is equal to, so the inner function differentiated is going to be this differentiated here. So x differentiated is 1, and the natural log of 2x differentiated is, so we talked about this in the first video in this chapter. If you have y is equal to the natural log of kx, dy over dx is equal to 1 over x. This k doesn't actually really have any effect. So the differential of the natural log of 2x is still just 1 over x, like this here. And this is multiplied by the outer function differentiated, so this power of 3 here. So this power of 3 is going to become the coefficient, so it's 3, and then remember this inner function stays the same, so x plus the natural log of 2x, and now it's going to be to the power of 2 instead, and then we can move this 3 to the front. So dy over dx is equal to 3 times 1 plus 1 over x times x plus the natural log of 2x squared. Okay, so here's one final exam question for you to have a go at. So pause the video, have a go, and I'll go through the answers in about 5 seconds. Okay, so we talked about tangents in a year 1 differentiation video titled Tangents, Normals and Increasing and Decreasing Functions. So go back to that video if you need a reminder of how we find the equation of a tangent. But in order to find the equation of a tangent, we first need the gradient of the tangent. And we can find the gradient of the tangent because the gradient of the tangent is the same as the gradient at this point on the curve. So we need to find the gradient at this point on this curve here. So therefore we need to find dy over dx. Now at the moment it's in terms of x, and we can't really rearrange this in terms of y. So we're going to have to do the thing where we need to find dx over dy first, and then use the formula that dy over dx is equal to 1 divided by dx over dy. So we need to find dx over dy in order to find dy over dx. Remember, to get the gradient we need to use dy over dx. Now for this here we're going to need to use the chain rule. So the inner function is this 2y plus pi, and the outer function is this cos here. So the inner function differentiated is 2y plus pi differentiated, and this 2y here will become 2, and then this pi here will just go away. And this is multiplied by the outer function differentiated, so this is cos differentiated, which is minus sin, and then this is still going to be 2y plus pi, like this here. And we can rewrite this as minus 2 sin of 2y plus pi. So dx over dy is equal to minus 2 sin of 2y plus pi. And therefore dy over dx is going to be equal to 1 divided by this. So dy over dx is equal to minus 1 over 2 sin of 2y plus pi. And therefore, in order to find the gradient at this point, we're going to sub in the y coordinate at this point, because this is in terms of y. So we're going to sub in pi over 4 as y, which we've done here. And if you put this into your calculator, remember we work in radians when we're subbing values in the derivative. If you put this into your calculator, you get out a value of a half. So the gradient of the tangent is equal to a half. So in order to find the equation of the tangent, which is a straight line, we have to use the formula for a straight line. Now we talked about this in the equation of a straight line video back in year 1 in chapter 5, so go back to that if you need to. For this we need the gradient of the line, and we also need one coordinate on the line. Okay, well we know the gradient of the tangent is a half, so we know the gradient, and we know a coordinate on the tangent as well, because we are told the tangent to the curve is at 0 pi over 4, so therefore it will pass through this point, as this is the point in which it touches the curve. So therefore this is the coordinate that we're going to use. So we can sub the values into this. So it's y minus y1, so it's going to be y minus, then y1 is the y coordinate of the point that it passes through, so this is pi over 4, and this is equal to m, which is the gradient, which we figured out to be half, and then x minus, and then x1 is 0 here. So we can just write this as y minus pi over 4 is equal to a half x, and it wants it in the form y is equal to ax plus b. So we're going to move this minus pi over 4 onto the other side, so it's y is equal to a half x plus pi over 4. And this is the equation of the tangent in this form here.